Is everyone done with this? Yeah. Can I remove here now? Okay. But we still have 2 minutes till they get. Yeah. And in the meanwhile, if someone from Trondheim is watching us, if they can send me a message so that I get to confirm from them as well that is everything working from their side. Okay, it's working from there as well. Let's see if we have. See some more messages from you. Okay, it's 14:15 now, and you might have done your attendance here. From the week first, we saw that a brief introduction about the course. It was more like administrative kind of thing, how the class will go. And now, today, we will be going into actual crypto. And here we have the crypto systems, cryptology, which we will start from today. And this will contain actually 3 weeks from now. In the week first, that's today, we will see, history about cryptology, how this has been started and how people have evolved in cryptology and now where we are in cryptology. And second week, we'll go with symmetric crypto. And the third week, we will cover hash functions and asymmetric crypto. Although this overview slide, I have created this, there may be some additions to these subheadings as we go evolving new terms. We will be including them here as well. So coming to this history part, that cryptology, it has actually two main terms. One is cryptography, and second is cryptanalysis. This cryptology, if you can see, is formed of two words. One is crypto, which actually means hidden or say secret, and graphy is writing. So if we see that from this word only, what cryptology is, writing something in a secret way is called cryptography. Why we need to write something in say a secret or hidden way? Is there any reason? Can any one of you tell me, is there any reason why we need to write this in a secret way, or say in some hidden patterns? Yeah. Yeah, exactly. So that others will not see what we are saying to other people, which is not intended for them. So that the information that we are sending across the public channel, that is internet nowadays, will remain hidden, will remain secret. So here is one of the definitions that what the cryptography is. It's actually we are sending something, transmitting some information in a way that others should not understand this. It should be understood to the people for whom it's intended. Okay? But I also said that there is cryptanalysis as well. That this is the sort of process to knowing how this text has been converted into some hidden form. Cryptanalysis, you can see, you can say, for example, if some text has been encrypted so that others cannot read, and cryptanalysis is the process of knowing that crypttext, that ciphertext, what we call it as. I will tell you ciphertext in a few more slides what that is. So there are two terminologies, cryptography and cryptanalysis. Cryptography is being done by the people who deal with security, say what we call as good people. And cryptanalysis is the job of hackers who actually want to get into the information. So these are two definitions. There are other definitions as well. If you can Google it, there you can get different definitions. And these were in the previous slide, so I put them here as well. Now, this cryptography, cryptanalysis, or say security is based on some triad. What we called here in the security is called CIA triad. C stands for confidentiality, integrity, then authentication. Confidentiality means if we are sending a message, are we sending this message to the person who should read it? That means intended for the receiver, for which I'm writing something. Then integrity is the accuracy. Whatever I'm sending, is it accurate? For example, if I say, I can say any information in public, and for example, I will say from tomorrow we will take the classes at time 10 in the morning, and the information is for public. What it is, integrity is, if someone has not changed the text and said this instead of 10, the class will be at 12. So what is the correctness and the accuracy of the message? That's called integrity. Then we have authentication. It was actually availability because of the people working on the authentication at our group. We put it, you can put it in authentication term as well. It is actually the knowing of sender and receiver, knowing of two parties, their authentication, whether they are the same person whom we are taking the data, or if there is not someone else who is sending or receiving the data. Then some more terminologies. These are the things that you will see in coming slides. that what the plain text is. It's just an information, just a text that we need to send across to the public channel. Then ciphertext is information. The plain text is simply that we can also understand, everyone can understand. If you send something to me, if in between someone sees that, he can read it, he can understand it. But ciphertext is somewhat which no one can understand except the people who are sending this, because they internally have some mechanism to put a plain text into a ciphertext. Then comes algorithms. These are just methods of converting this plain text into the ciphertext. For example, I have a text I want to communicate with a person, say at the corner. So I don't want to other people to listen to the message. So what I do is I convert into a ciphertext, then tell everyone to pass that text to the people I want to talk. Then no one can understand the ciphertext, but at the end, who receives the message and has the mechanism to know what kind of ciphertext it is and how I can understand this, will be able to read that message. And those conversions is by using these algorithms. Algorithms are actually these decryption and encryption algorithms we have in this what we call as cryptography. In encryption, we simply convert a plain text into a ciphertext, and decryption is the reverse of that. Decryption is simply converting that ciphertext back into the normal text. So if I tell you, who will do the decryption, sender or receiver? Decryption is being done by receiver. Why? Yeah. To understand the message. So obviously the message that has been converted or encrypted by sender, he used the encryption. Then the decryption is being used by the party at the other end who want to listen. Then we have what we call as key. Key is actually the secret input to the encryption and decryption. If everyone knows what is how it has been decrypted and encrypted, then there is no way, there is no fun of doing this security kind of thing. That's what we call as we have a key. Only key is known to the people between whom this information is being transmitted. That means encryption key, if I tell you that the key is this and information is this, there is no way to know the information by the other people unless and until they have the keys, the encryption keys or the decryption keys. The basic terminology that we can see here is, if you can see here, the message, which is a plain text written, hello world, and at the sender end, say we will not call it a sender or receiver end, we will consider this as a process now, encryption, decryption process. Here, if you see, here at the encryption side, we have something what we call as key. If you can see here, key. Then after encrypting the hello world message, it will be converted into ciphertext, which I think none of us can understand here, because we already know it's a hello world. That's why we can say randomly this is hello world. And from the decryption side, the same thing is being decrypted using the same key. If you can see here, using the same key to get the original message, which was hello world. This is the terminology that you will see throughout these slides, and this is the what I call this is the main slide to understand the process of this encryption and decryption. Okay. Now we have in the security, especially in cryptography, we have some very well-known people which we use for our encryption and decryption. These are actually the characters that play a nice role in helping people to understand this cryptography and cryptanalysis and say cryptology. Do you know any of them? Have you ever heard the name of any of the character? No? Do you know Alice? There are characters, you might not be knowing them. There are Alice, the Bob. They always want to talk to each other. Yeah? Who got it? Yeah. You know Bob only?
No, I don't know.
Okay. She's Alice. She wanted to talk to Bob on the what we call as public channel. And unfortunately, there's Eve, who is what we call as very nosy and always trying to know what else want to say to Bob. And whenever there is some communication between them, she puts in, and she wanted to know what is going on there. There are some more characters apart from these three: Carol and Dave. These are all the characters in cryptography that we will maybe not see the faces, but we will hear their names. Now the thing is, Alice want to talk to Bob and send a message to Bob on a public channel. Bob is waiting for the message, and whenever the Alice is sending the message, there is the guy in between, already introduced. She always wanted to know this. The process is, when the information goes from Alice to Bob, you will see it. Now, our motive is to, Bob should get the information, Alice should not. That means the text, that whatever it is, should reach to the Bob, but not reach to the Alice. Now, here starting the history of cryptography, their historical background. Started from Leonardo da Vinci. Then there's the Voynich manuscript. Then comes the Caesar cipher. Then we will see simple substitutions, Vigenère cipher, then transpositions, then few more things that we will see. The first two are not actually the crypto systems. Leonardo da Vinci was an Italian polymath who is widely known for the greatest painters of all time. He used to paint a lot of things, but whenever he wants to send the information to the people, and he don't want other people to see that, he used to write in this way. Do anyone know what way he was using? Although this was some language, if he has written the language as it is, people of that age may know the language, they can read it. Any of you have heard about what he was doing to send a message? No? He was actually using the mirror to write the message. And starting from right side of the page, moving to the left. Then he was giving that information to the person who was carrying the message. He was not able to read it because everything was written in the reverse form. And the person who for whom it was meant, he was already knowing that I have to see this in the mirror, or I may have to read otherwise. Okay? Then there was one more Voynich manuscript. People claim that this has been decrypted. The information has been revealed. But till now, most of the other sites claim that it has not been decrypted at all. Some of the parts may have been revealed, but some parts are there to unreveal. It was named after a person, Wilfrid Voynich. He was actually the dealer of books. He was selling books and buying books. And he was Polish, and after his name, he found that book, and after his name, it was like invented kind of thing. Most of the pages in this book was just diagram, just illustration. So people who are interested, they have a link here. They can you can go and just give it a try if you can crack it. Yeah. Some more terminologies. We have encryption function, that I already told you what encryption is. Here, if you can see that we have a message M, and K is the encryption key, which changes that message into a ciphertext C. Got it? Simple? Simply, we have decryption. For decryption, we take the input as ciphertext C, and which outputs the actual message M. Yeah? These are the important things that we should remember here so that we can apply in other slides. Modulo calculation. Do you know modulo calculation? Any of you don't know? Everyone knows the modulo calculation? Yeah? It's simply if you are interested in the remainder part of a number. For example, if I say, say 19 modulo 3, it simply means subtracting the 3 from that number again and again until I get the number which is less or equal to that number, say less than that number. That is the remainder part that we call the modulo. Okay? Can anyone tell me what's the modulo of 17 mod 3? Apart from you people. Who else? Yeah? Anyone else? Yeah? Okay, what's that? It's 2. If you continuously subtract this 3 from the 17, you will end up with 2, which you cannot subtract with 3. Yeah? Some more things about modulo, how to calculate that modulo, and you will see in future slides, this modulo is important in few of the ciphers. How to calculate 954 mod 73. Okay, and it's a homework for you people as well to see some tunes or something about modulo. Yeah, so that it will help you in your assignments as well. As you might be knowing that today you'll get an assignment as well. Yeah, surprise. Okay. Then this modulo follows the rules of normal calculation as well, which is good, which can be used for other things. The thing for you is that, although this was the example in the previous slides as well, assume that it's time 13. And what is the exactly 1,000 times after the time now? If it is 13, what is the time exactly 1,000 minutes from now? Can anybody tell me? Yeah. Good. And how you calculated? You got it? We have 1,000 minutes. That we know that an hour is 60 minutes. We divide it with 60 and we got, say, 16 full hours. Okay? Then for the remaining 40 minutes, it was 16 hours and 40 minutes, which we got. And if you do that 16 hours, it will be 13 plus that 16 mod 24, because we have 24 hours. Then we have to go back. Yeah? And then ultimately the remaining 1,000 minutes after 13 is 540, which is absolutely right. And I want you all, some of you know, but you all should see watch some tweets about that. Yeah. Now we have a first actual cipher. That is what we call a Caesar cipher. That has been named after the Caesar, who was the Roman emperor. What he did is he used 26 character alphabets. Do we have some more alphabets than 26? So it's good to say he used all these alphabets to write a message and to convert it. Message M is the letter A to Z, ciphertext. C is a letter which was also A to Z. That means he converted the message, which was in alphabets, to ciphertext, which was also in alphabets. Key, K is the letter from A to Z. That means it is a letter that can be either A to Z, any letter. For Caesar cipher, he said that K is 3. That means every word from the plain text is shifted 3 digits. Okay? For example, A will be converted to D, B will be converted to E, and likewise other alphabets. Clear till now? He used characters, then he used a shift. How much shift he used? D equal to K equal to 3. Then, since computers cannot process these characters, what is being done is we converted every character into its numeric form. That means A0, B1, C2 to represent in the say what we called as a computer understanding form. Then what was the encryption? Encryption was the message here with the key K. That is actually the message plus that key, isn't it? Message plus that key. For example, if I say 0 was A, then plus 3, what was that? D. Simply he used for the encryption. And M plus K, that is mod of 26. Why the mod of 26? Because we have 26 letters, and as we did in the previous example in the time, if somehow we reach to the end, it will come back to the first position after 26. Okay? Then for decryption, same thing. He took the message and subtract what we call as key from it and calculate the modulo of that with the 26. Okay? Then we can say that if I have a message, encrypted message, I will use the key. After subtracting to that message, I will get the actual message. Yeah? So he did the mod function like this, which is nothing but just in case of encryption, he's adding to the number, and in case of decryption, just subtracting to that number. Yeah? This is just a function. If you can implement it in MATLAB as well, it's just a matter of one line code, and you can get the implementation of Caesar. So decryption of the ciphertext C with the same key leads to the original message M. Okay. For example, we have a message hello, and we have to encrypt it with the key D. Say D equal to 3. Can you tell me what will be the other digits in HELLO? H I told you, it will be K. Yeah? Can you count the for others as well? Yeah? Give it a try. What will be the decrypted, encrypted text for E? Yeah? Using the same procedure above. We have D equal to 3. We already know that H is 7th. Yeah? Then if we see D plus H, that is actually nothing but the K letter. That means for H, the encrypted letter will be K. And what will be the encrypted letter for E? Yeah. How you calculated that? D will be same, 3. What is the value of E? Because we already said that all the characters have been changed into numeric form. That means A is 0, B is 1. Yeah? Yeah. 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 Are you getting this? Do I have to repeat? Okay, tell me then what will be the ciphertext for L? Who else? Isn't it easy? What is D? D is 3. Key is 3. Yeah? Key is 3. And we have to see what plain text character is and its value. Key plus that value, that means 3 plus that value, will be equal to the ciphertext. Who will tell me for L? Not you. Who will tell me for L? Yeah. Is it okay? L O? Do you agree? Yeah. And for this next L, it will be the same O. And for O, it will be? Yeah. Everyone got it? Yeah, do I have to repeat this? Okay, good. So you got to know how this message has encrypted. Yeah? The total for hello was Kahoor. Okay? You know the process, how it has been changed. Now we can have a sort of, say, grid which can tell us which character, although it took time for some people to calculate, but we can have a grid which can tell us what these things are, how we can calculate them. Yeah? Apart from calculating, we have only, if you go there at the top this row, these are nothing but the characters in the actual message. And if you go at the left column, these are actually key, and in between you can see the character, the encrypted character. For example, what I told you earlier, that for H with the key D, yeah, with the key D, why it is, if we see here, we have to see character, it is H with the key D, and it will be here. What is that intersection point? Can you see it? Can you see it now? Yeah? Is it getting clear now? It's here. Yeah? To show you more clearly. Yeah? And same thing, if you see for the plain text E with the same key, that's D, the encrypted text will be H. Yeah? Same for others. Now we have the decryption. We took the same word, that means this Kahoor that we got as encrypted text, we have to convert back that to plain text. What we do is, we take the same key, that is D, and go along to the K, where we have here, if we take the same key, that is K, from here, then you can see that the H that has been written is actually character. That was H from here. You got it? Yeah? If you take the same key for the encrypted text K, same key, that is D, from the leftmost column is the key column. Yeah? From there you take the key D and take the ciphertext K, reach to the K, because these are all ciphertext characters, reach to K and see at the top which plain text character it is. It has been converted to H, then E, L, L, O, back to hello. Yeah? You understood this? Any confusion in this? Okay. Is there any kind of security in this? Yeah. Do you feel this is secure? Yeah, because it's just a key of one character. If key is leaked, everything you can change. You can convert back to plain text. And there are not that much combinations because we have only 25 different keys. Yeah? Let's take the example of this thing. This is the ciphertext. And you have to change into plain text right now. If we see that the word, the first word here, the first word here, we are saying how people can actually break these things. Yeah? We have the first word here, and if we take all the shifts, we don't know the key is 3 or 4 or 5 or 6 or 25. Yeah? Then we take all the shifts. Say from L, we take all the shifts up to 26, whatever the possibilities are. And we got this long table, long grid. Yeah? If we see this grid now, there is some junk words we don't know, but there is a kind of thing that we know probably. That is the information. And where I got the information? Exactly after 23 shifts. Yeah? Or I can say in the reverse, it is only 3 shifts. Yeah? Once I got this information, I got everything from those shifts. Got it? Because there was key is known. If you can put the shifts, you can somehow encounter, if it is written in English, you can encounter the words. Or I think if it is written in other forms as well, there may be shifts only. Yeah? So, does not change the statistics, because if you see the shift, it will always be the same shift, because 3 will be always their key. We have these words, most common letters in English. If you don't know, I will tell you that these are some of the words, E, T, A, I, O, that are mostly used in English. Yeah? And if we have a pattern, and if we see what are the most common things, what are the frequencies, we came to do what we call as breaking of this cipher. Yeah? What we do is just frequency analysis. Frequency analysis, we already know that which words, which characters have been used mostly in English, as we have them here. Yeah? Using this analysis, frequency analysis, or what we call as letter frequency, we can break into this Caesar cipher. For example, let's take this example. The histograms above are actually the text that we just saw, and their frequency of words there. Yeah? And at the bottom, you can see the actual frequencies of English letters. Yeah? We can do a kind of pattern matching. For example, we will see, can we find some kind of patterns in these 2 histograms, so that we will come to know that which letters have been used. Yeah? So can you see anything common? Can anyone of you see anything common in these things? Any part you can see? Yeah. Yeah, we have to see actually the common patterns between this and this, so that we will so that we will see if there is some pattern. We already know these are English characters. From there, then we can know that which English characters have been used there. Yeah. There is one pattern that I have seen here, is also in actual English frequency pattern. Yeah. If you can see this pattern, can you see? There is, say, this high frequency, then low frequency, low frequency. The same high frequency, low frequency, low frequency. Although it's not exactly, but the pattern is there. Then with the low frequency, high frequency, low frequency, high frequency. This way I came to know that there is something same that has been written in that text, which is what we call as, we can see here as well. Yeah. Similarly, if you can see here, yeah, where you can find this pattern in this English patterns, English alphabet patterns. Yeah, it was this. Okay. Now, I saw these patterns. What you can tell about these patterns? Any idea what we can say about these patterns? We got patterns from English and from the text that have been written. If you see closely, that at the position, say 8 on the text, on the cipher text, there was high frequency, and same thing we can see in the English text. And 8 is nothing but an alphabet, and if we convert every alphabet from A to 0, B to 1, we got this 8 as H in the cipher text. Got it? Well, some faces are very surprised. I don't know. You got it? Yeah? It tells us that E in the cipher text, sorry, in the plain text, matched to the 8. E, which is actually here, E here, this one, in the cipher text is matched to 8. Yeah? So how I can say K equal to 3? If E is 8, K is equal to 3. What is K? That means the key. Yeah? That means it has found one of the alphabets, so it can crack all those. Now, Caesar cipher is easy because it has only 26 alphabets, so you can have only 20, say 25 or 26 keys only. So there are possibilities where we can have multiple keys. Say we can have more than 26. We come up with some permutations, yeah, where we can have a plain text, we can have a cipher text, Yeah, every word will be converted to new word. This way, you will be having 26 factorial instead of just 26. Yeah. As you can see here, this on the left side is the plain text, which has been converted into ciphertext, where say A equal to B, B equal to N, C equal to some things. If we do same kind of thing, this is what we call as substitutions. Substituting one alphabet with the other with the other. That in total we have how many options we have there instead of 26? 26 factorial. If we have this encrypted text, yeah, and we need to see what this encrypted text is. Maybe it has been not with the d equal to 3. It can be have the substitution methods. Yeah. Substitution methods is simply using other letter instead of plain text, but there will be text only. Yeah. So this is the encrypted text that I want you people to give it a try and see if you can see what this is. All I can say about this text is it's about tempest testing. Yeah. Do you know what is tempest testing? Tempest testing. Tempest testing is actually testing about electromagnetic devices who actually emit radiations from them, or say a kind of all electronic devices, and to see their radiativity functionalities or radiativity efficiencies, characteristics. That is tempest testing. This topic is all about tempest testing. Yeah. Take a 15 minutes break, and in the break, think about it. We'll come back and see who can tell me what this is. Yeah. Okay. Is everyone back? Okay, welcome back after the break. We were talking about tempest testing, and you have been given a text, which is ciphertext, and I told one thing about this, that this is all about tempest testing. This topic is about tempest testing, and you need to know using the substitution methods what will be the actual plain text of this thing. Yeah? So have anyone tried any of the letters? Yes. Okay. You said that. Oh, can I did it here? You talking about this one, huh? Okay. He's saying that he came to know that these two words are tempest testing. And how we came to know this? Yeah. If we see that in tempest testing, the arrangement of letters, that is letter 1, letter 7, and letter 8, and letter 11, they are same. Yeah? That is T. Similarly, letter 2, 5, and 9 are same in this keyword tempest testing. Yeah? Letter 6 and letter 10 are same. Then letters 3, 4, 12, 13, and 14 are unique. What it says that if we have a pattern, like we have tempest testing, we found it that here T and I has been replaced in the actual ciphertext, which you can see IYXOYLI something. Yeah? Then the second part of that word, IYLITDY, TDV. Yeah? So it has the same pattern as tempest testing. Okay? So I can replace that with tempest testing. While replacing that with tempest testing, I came to know all the other characters. Not all, various other characters. Yeah? And some of the informations I can just, with the help of my English knowledge, can substitute. For example, if here in the green you can see it's IN star 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 M star TI star N. What it can be? Any guesses? Yeah? Information. Yeah? See? It's the same as exactly above. So I can convert this into information, which will help me to reveal various other characters. Yeah? Similarly, we have this. As I told you that there was something related to radiations, electromagnetic device. Yeah? Yeah? This is substitution. You can just guess, you can see what words can fit there. This is all substitution. Yeah? Then slowly we can start reconstructing everything. Then last word is reconstruct. Then we have, there is one alphabet missing. Yeah, we can guess that as well. Then we have LEA star ED. What it can be? What are the possibilities there? Yeah? Maybe there can be several possibilities to this word, but we have to see the actual where it fits, what it fits there. Yeah? It was actually leaks. We could have guessed leads. Yeah? But since it fits with the context, we can substitute it. See, this is all about substitutions. 23 letters of the key and other letters are not used in the plain text. Yeah? We read about Caesar, we talk about substitution methods, and can you differentiate them? Can anyone tell me a single difference between substitution method and Caesar cipher? Yeah? Yeah. Yeah. But this is the difference. So can I say that all the substitution methods are Caesar ciphers? Can I say other way around? Well, Caesar cipher is also a substitution method. Why do you substitute one alphabet with the other? But there you have a limit. There are substitution methods. At the end of this today's presentation, I will give you just an overview of the structure, how this cryptology and symmetric asymmetric is going, so that you will get a good picture, which will help you in your assignments as well. Yeah? Anything more about the difference between these two? Yeah. Mm-hmm. Yeah. Yeah, because you have key, you have a single alphabet there. Yeah, and that is that is known, you can convert everything back. Yeah. And in Caesar cipher, each letter in the plain text is replaced by the letter some fixed number of positions. That we already said. Now we have something what we call as Caesar cipher. Sorry, this Virginia cipher. In Caesar cipher, you have what we call as monoalphabetic pattern, monoalphabetic nature, in which each plain text character is always replaced by the same character. If I say that A will be replaced with the K, it will always be replaced with the K. Yeah? The alternative is polyalphabetic cipher, which is, say, Caesar cipher. A plain text character can have multiple ciphertext characters. Example, there we have, say, instead of one key, instead of one ciphertext, we have a key of length R. Say, for example, there is a plain text that Virginia cipher is polyalphabetic, and for this I had a key that was actually crypto, but I keep putting on crypto until I completed all the characters which were in my plain text. That means the first C is replaced with something, the same C is not replaced again with the same thing. Yeah, then there will be some different character. Then for this ciphertext, we will be having, this was the key, we will be having ciphertext like this. Yeah, because we already used this table. Yeah, instead of using only one alphabet, we are now using multiple alphabets. Yeah. This gives a bit more security, because at the beginning, if you know that key is 3, you can crack everything. Now you have to work a bit more to decrypt this. Yeah? And same procedure you know here, how it has been converted to ciphertext. Anyone has doubt in this? Any? Okay. Vigenère is broken if the length R of the key is known. There, if we know the key, that everything was decrypted. But here, if we know the length of the key, we can again use that frequency analysis. After how many words the same keyword we are getting, or we can do that statistics to know what this is. Yeah? Because whenever someone builds the system, they put the security, and once it's cracked, the new system will be built which has the more security than this. Like the Caesar and substitution, they have the way of what we call as mono-alphabetic character, which was easy to crack. Then Vigenère, it also has, say, what we call as drawbacks, that if we are known to the length of that key, we can do the statistical analysis to know the key, yeah, to know the pattern. For example, here, if we came to know that this C has been actually came from V, we can do a kind of analysis after how many alphabets the C is coming again. If we got that pattern, we can somehow came to know that this text is what we call as the ciphertext of the plain text. Yeah? For example, first pattern, he saw V here. In the next, he will do it for I after doing the same shifts. Yeah? So there is what we call as the technique, actual technique that is used to decrypt this. Although this is not very seriously for you people to read this, there is something which can be used to decrypt the Vigenère cipher. That is what we call as index of coincidences. And if you can note this down and read it, what this is actually, and later on, if you have time, we can discuss that. Yeah, that's why it's not highlighted much. You can do it. After Vigenère, there comes the new Burnham, which was called one-time paired cipher. Burnham cipher is a special case of Vigenère cipher that we just saw. Length of the key is same as the length of the plain text, and the key is never reused, which was the actually drawbacks of the previous cipher. We had the crypto key, and we were using the same crypto. Here, for example, here comes Alice. She wanted to say something to Bob, and she sent a text which is give. Okay? And the key was UNMR. We have here, why we can decrypt what this is. Yeah? This you already know. The ciphertext for this is AVHV. Can you see the ciphertext this? Is this clear for everyone, how we came to know the ciphertext from this table? Yeah. But this ciphertext will be seen by our favorite character. Yeah? And for example, she guessed the key is ABCD because she don't know the key. She has seen the ciphertext, and she will try, because she also has table, she will try ABCD, a random key. Yeah? She will get the plain text ACJY, which is, oh, it's not of meaning, it cannot be key. Yeah? What will be her next step? To select some other key. For example, she came up with the key TFDJ. Is a guess, again guess. Yeah? Can you tell me what TFDJ will be? If the key is TFDJ and we have a ciphertext AVHV, anyone, can you tell me what will be the message then? Yeah? Got it from here. Okay. Yeah? Can you calculate this? Can you tell me what the text the E will get? Yeah. T. Yeah. Anyone else? This is simple. You have to see the table. Yeah. Yeah, thank you very much. She managed. It is take. Yeah. And now the E will think that, oh, it's an English word. I got the message. What else wants to say to the Bob? But since this is the English word, the actual message is not correct. Then Bob will get the same ciphertext. Bob will get the key, and obviously Bob will get the exact key, and he will get the exact message as well. So this is how this word name cipher works. You have a key, and that key cannot be reused. For example, we have 5 letters key that we are actually using for all our ciphertext, plain text. Here we have the plain text, which was 1, 2, 3, 4 characters, and our key was also 4 characters. Yeah? So it gets more complex to break all these things. Now there are rules for encryption using word name. Plain text plus key equal to ciphertext. Yeah, very easy. Decryption formula simply ciphertext subtracting the key, you will get the plain text back. How it works? We have a plain text which we want to convert. We will come up with a random key, and the random key will be, the length of random key will be the length of our, say, plain text. So do you feel any say drawback here? If I say I have to convert, I have a complete book that I want to convert into ciphertext, my key will be exactly of that book. So I need to have two books, one for my plain text, second book will be completely my key. Yeah? Key length is always equal to the length of ciphertext. Now rule is this third line, after adding the plain text and keys, if the number is greater than or equal to 26, then we subtract 26 from the ciphertext in the encryption. Here is the table we have, and we will follow an example from this table. We have a message hello, and we have the secret key XMCKL, yeah, which can help us to convert our message into ciphertext. So what's the first step is, we will see the numeric values of our message, yeah, and the numeric value of key, that is from the table. H will be 7, E will be 4, L will be 11, then again 11, then 14. This is the numerical values of the message that we want to send. Then we have the values for our key. What is the second step? Second step is, we just add them up, both key and message. Yeah, simple. We add them, and as the rule said, if we are getting some alphabet which is greater than 26, what we need to do? We will subtract the 26 from that. Yeah, and we will get ciphertext. Got it? Easy? So can you get the actual plain text back from this EQ and VZ? What's the procedure? What's the procedure for decryption? Yeah. For encryption, what we did, key and message, we add them up. Yeah. And for decryption, isn't it like we subtract the key from them and get our text? Yeah. For decryption, we have the ciphertext. Be attentive, it will be in your assignment. Yeah, today you will get an assignment as well. Yeah, we have a ciphertext. We have a secret key. Here is the values of ciphertext. Then we have secret key. Yeah. What we need to do now? Summing them up. Yeah. In encryption, we sum them up. Here we subtract. And if we are getting the values which is negative values, again we have to add 26 to get the normal. Yeah, we will back get 7, 4, 11, 11, 14, which was the actual message, actual numerical values of our message hello. Yeah. Got it? Clear so far? Now, few more points. That length of key is same as the length of plain text, and key is never used. Already said. Your num cipher is secure if used correctly, but not practical. It will be depend on the randomness of your key. The more random key you have, the more secure message you will get. You will be having. Yeah. Some of the drawbacks. So we have key streams and their distributions, which is like hard to manage. For the solutions, we have stream ciphers, in which we have key streams. Yeah? Yeah.
What about when you look at the linear
But there is not. It is not say alpha. Only one character is not there. You have the key which is as long as your message. So guessing a long message is complex than guessing a single character. Because yeah, nothing is impossible. Security people usually say that the security is an illusion, but the security you have, anyone can break it someday, somewhere. Yeah. But we can have everything. Like if we have a security systems today, it's not sure that tomorrow they will be secure. Yeah, we have updations to everything. That's why we have new ciphers. We have disadvantage in one, drawbacks or shortcomings in one, and we have advantage in new. And in the future time, we will see that there is security breach in them. We will come up with new. Yeah, yeah. Yeah, that like we give the example as well. If you decrypt that, but if you know the key, you surely come up with what we call as confidence that this was the actual message that I got from the actual key. But the people who used to say cryptanalysis, who used to get into these things, they get the message, but they are not still sure that we got the exact message. Yeah. So this was all about Varnam cipher. There are few more things, that is transpositions. These are transposition ciphers that if we have, say, what we call as drawbacks in one, we try to come up with the coverage too in others. Yeah. In case of transposition ciphers, letters or elements are moved rather than replacing. Yeah. For example, we are giving A and replacing it with some other letter. But here in transpositions, we don't do that thing. We actually rotate them. We actually move them in some other way. We will see those in examples as well before we see how it works. What it does, it actually breaks the text up in blocks of n letters and permute with secret permutation, sigma. We denote that with sigma. Yeah. For example, I have a plain text. How it works, we will tell that thing. Plain text I have, and let n equal 5. What's n? Is the blocks, how many blocks I want out of this plain text. And sigma is the pattern, in which pattern I want that. So after I break this message into the 5 blocks, into 3 blocks with the 5 alphabets, then I will create a grid with, say, 3 rows, because I have 3 characters now, 3 words now, and with 5 columns, and I will fill that with the information, with the actual information plain text that I have, and using this permutation, I will rotate these columns. I will come up with this. Yeah? You got it how I rotated this? Yeah? Everyone got this? No? Where mark is there? What it was? For example, if I say here, we had 1, 2, 3, 4, 5. Is this visible to everyone? Yeah? I have all the letters in it. Yeah? Now I want to convert that into the pattern that we have, 3, 5, 2, 1, 4. Say 3, 5, 2, 1, 4. That means the next grid that I will have 1 as this. That means it will be that column. Yeah? It's simply replacing that. Then we have 2 YRC there. We have, yeah? Then which one is third? COH. Fourth? And then fifth? Yeah? That's just the permutation, rotating of this thing, so that we will come up with a mixture of actual plain text. Then I need to convert into permutes, what permute I get out of that matrix. If I read that in a rows, it will be PVCTR. Yeah? What will be a second? What will be second? I need to write this. Is this visible? I wrote it PYCTR, then this AROPG, then ACHLI. Yeah? That will be the permutes, and that can be the actual ciphertext as well. Yeah? If you see here, sorry. Yeah. AROPG. Okay, yeah. Yeah, you got this? And which I combine will be my ciphertext. Yeah? We have a n, which is actually length of block. Then we have a permutation function, which is actually a pattern of that blocks. Then I can convert that back into my permutation ciphertext. We can also use n by n matrix, in which we can write in the same way. If we have a long text, we can write in, say, 2 or 3 matrices. Then we can use the same procedure to convert that into ciphertext. Say, for example, let n equal to 5 again, and I have the same this permutation pattern. And plain text is information security is an exciting topic for study. Yeah? How can I convert that into n by n matrix? Anyone? Simply, I can have 2 matrices, because one is 1, 2, 3, 4, 5, and 5 by 5. Yeah? if you can see the information is filled as it is, information security, here, you can read it like this. Yeah? Now using the above given permutation, you convert it into two matrices. Can anyone convert it? Can anyone try it? Let's go this way. Yeah. Give it a try, and tell me what will be your, say, encrypted text. Yeah, give it a try. I will tell you what will be the encrypted text. Okay, other people cannot see this board at all. We're sorry, and I thought it is in the camera range. Yeah, because we are not the only people learning here. We have some other people as well. So sorry for that. I will try to, say, rotate it a bit. Yeah. And yeah. For the people who are watching online, and we just converted that matrix into its permutation form, which is given on the board, which is very simple. The next example is here, which I have given you people to show me the ciphertext two matrices, so that I can tell you what the ciphertext is, to see how far you can go. This is very easy. Yeah, anyone? Anyone got that ciphertext? Yeah. Till the people here do the ciphertext kind of thing, I will have to repeat that again. For the people who are not able to watch this, okay, do I have marker here? that we already had a plain text matrix, and we have been given that was equal to 35214, and we need to convert this into that pattern. What I wrote is actually that same thing I wrote on the top of that matrix and converted it everything here. I start with this numbering now. So my first row will be, first column will be PAA, my second column will be YRC, my third column will be COH, and my fourth column will be TPL, and the last column, which is RGI. And the second step was we need to read it the row wise and write it down. And we did that PYCTR AROPG, then ACHLI, which was nothing but the ciphertext. I hope now they understood what we draw on the board. Yeah? Okay. Coming back to our slides. Anyone got something? Okay. No issues. Here we have a ciphertext, encrypted text. If any one of you want to confirm what they got, you can. I just simply, with that procedure, I converted these two matrices into on our permutation pattern, and just start reading from the top row up to the next matrix. We got this. And decryption process goes the other way around. We have again that block size n. Then we have, say, our permutation pattern, which was 35214 again. And for this, we have something what we call as ciphertext here. And for this ciphertext, we need to say what will be the actual plain text. Yeah? For the decryption, what we will do is, again, we will create this time with the ciphertext. If you can see, is it okay? Is it okay for everyone? Can anyone find any of the errors here? No? Fine? There is something, a mistake in the slide, if you have noticed. Yeah? Yeah. Yeah. Because by mistake, this is not deliberate. By mistake, this I've written two L's instead of LI. Yeah? And whatever ciphertext you have to write in them in columns. And after writing them in columns, you have the permutation pattern. The permutation pattern will convert this text into something like this. Yeah? And from this matrix, you can read in the same way from the top row. And what this message can be? I mean, what this message is? Can you read it loud, anyone? Yeah. Yeah, this is the message. Yeah. You understood this? You have any questions so far in the previous slides? Then we have something that is what we call as router machines. These are also used as ciphers. I actually wanted this portion you read it by yourself so that we can discuss things as well. Because once we discuss things, the other things gets clear, and you come to know not from on these slides, you will learn from other web sources as well. But still, after this presentation, we will be having one more break than presentation that will be on assignments. All about assignments, how you have to design your assignment and how you will be submitting. Everything is written, and tonight I will upload that assignment as well, because that is a presentation, and I will upload that with the name assignment, and you will be giving the time to submit that assignment. Yeah. So router machines, this is Enigma, is a router machine which is constructed of usually 3 routers. Now there are some with modifications as well. Once you hit a key, it will go to these routers, and with the internal mechanism, it will give you the signal on these light bulbs. That's what was the encrypted thing of that thing, that key. There was bulbs on the interface of that router machine as well. There are Enigma, Lorentz machine. These are router machines where we have inside them different kind of routers. If you rotate one router, how it will affect the rotation of other router, and what pattern will it come up with. That will be your, say, what we call as ciphertext kind of thing. If you hit A, it will go inside the routers with some combinations, some patterns. It will come up with some, say, encrypted pattern. Yeah. I will tell a few things about this. Then you will read these slides, because I wanted to complete these assignments. Sorry, these slides today, because this is the first day of your assignment, and you have to know everything about that assignment as well. Yeah. But I will spend few minutes on this as well. This is the inside single router, how they look like, their wirings and all. And once you press any key, say for example on a plain text, I will if I say I will press C, and on the ciphertext between the router, it will be converted to E. Same with other things. So it has 26 keys. So for every key there will be some other key apart from 26 only. Yeah. There were some modifications to these routers. Here with 26 keys, then stacker, Then we have different routers, right router, middle router, left router. Then the last, what we called as, which actually gives back to signal from these routers, which will give you the output on the same interface. Yeah. So for example, I hit a key here. Say it's A. It will go with the stacker. Stacker is nothing. It actually combines your key with the other output so that it will go to the router. It will encounter the first router, right router. Then again some pattern change, some combination. Then go to the middle router. They are actually fixed kind of these links. Once you hit one, it will rotate. It will give you the answer and it will rotate. Next time it will be different. Yeah. This way you will come up with, say, for example, if I hit A, it will be A, B, C, D, E, F, somewhat. It will be like P, Q, R, S. Yeah. So this is the functioning, how these routers work. This is the inside of a router. If you rotate one of the wheels, after complete rotation of one wheel, it will rotate other wheel. Or say some patterns are like after completing two rotations, it will rotate the second wheel. Yeah. More inside here, these wirings and these lighting bulbs after the rotation. For example, if I press a button at A, it will do some mechanism inside and it will blink that bulb, which was the encrypted text for that. Yeah. For example, here A, it will be giving, it will be blinking the bulb G. That means for A, after using these 1, 2, 3 router machine, it will give me the G as an encrypted text. Same after the change, after some change, if I hit the A again, this time it is giving me C. Yeah. This is more inside how they work. There are few more slides on them. Yeah. How it works. Maybe if you can see these things. Yeah. This is simple, and there are some 2 links where you can see the more content about these things. These Enigma machines. There is one Lorentz machine as well. These are coming under the category of router machines. There are Enigma 1 and Enigma 2. Second one is somewhat advanced than the first one, the simple one. You can have more information about these router machines. Yeah, and if you have any questions regarding them, you are welcome to discuss. And we will see those machines in detail if we get some more time. But till now, you have to go through these remaining slides by yourself. Yeah, and if you have questions so far. Yeah. Any questions? Do we have any questions from the people online? Yeah, it's better now. Do you want to take one more break and come up with fresh mind to see the assignments, or you want me to continue? Yeah. Okay, let's take 15 minutes break. We will be back. Yeah.